Yeah, so moving ahead now. So as I was saying, these electrons, this all these energies are shifted. On the p side there is a higher energy, and on the n side there is a lower energy. So these are the energies of the electrons here on the n side, and these are the possible energy values of the electrons on the p side. And why this is raised, as explained here. Now, so we can say this is a p side here with these few electrons here, and n side here lots and lots of electrons in the conduction band, and this is the valence band of the p side with having lots and lots of electrons, and then this is the valence band of n side, which is not completely drawn, but then it will also have some good amount of electrons here. Now, which electron do you think will try to diffuse? Let's compare two electrons, because the electrons on the n side are large in number and electrons on the p side are small in number, and so the electrons would like to diffuse from this n side to the p side. So which electron is going to come? Let's try to understand this one. This electron would like to diffuse onto this p side, but remember what we discussed at the beginning of the class, that in diffusion process the energy of the electron should not change, doesn't change just by diffusing. It's like they are moving randomly, isn't it? So no change in energy. So if this electron would like to diffuse here onto the p side, there is no energy state here. We know that lots and lots of energy states are here in the conduction band. Lots and lots of energy states are there, possible energy states in the valence band, but nothing in between. We can't have an energy state in this forbidden energy gap. So this electron can't move here because no quantum state is available for it to jump or diffuse from n side to p side. Alright, so this electron, no chance. But what about this? How about this one? You can see here this electron, it can diffuse. Why? Because corresponding to this energy state on the n side, there is a corresponding similar energy state in the p side also. So this electron will be able to diffuse. So the electrons here will be able to diffuse, but these electrons, they will not be able to diffuse. So what we say in general is that these electrons are not able to overcome this energy barrier. That means if we want this electron to diffuse from this side to this side, first we should raise its energy from here to here and then make it diffuse. So for that raising energy, we don't have the energy for the electron, so no diffusion here. All right. And so it all comes down to these electrons beyond this, above this, these will be able to diffuse onto this side. But how many electrons are there actually here, and how many electrons are here there? So the point is that the electrons, the number of electrons having higher and higher energy is lesser and lesser. In fact, as we plot the number of electrons in a particular energy level or energy state versus the energy, it's exponentially decreasing. That means the number of electrons with higher and higher energy is simply very, very less. So number of electrons having a particular energy versus the energy, actually it's exponentially decreasing like this. So very few electrons here on high energies and lots of electrons here on the lower energies here. So as we go down into this conduction band to lower and lower energy levels, we find lots and lots of electrons, but these lots and lots of electrons can't diffuse here. So that is what is there in the p-n junction in equilibrium. So some diffusion takes place from here to here, and we know that in the previous class we discussed some drift happens from here to here, and drift from here to here and diffusion from here to here will finally balance. There is a concept of Fermi energy and Fermi function, which we are not going to discuss actually because it is out of syllabus. Alright, so moving ahead now. Now what happens to this p-n junction in the forward biasing condition? Let me just adjust this once. Yeah. Okay. So p-n junction under forward bias means that connecting the p-type to the positive terminal of the battery and n-type to the negative terminal of the battery, and this is the depletion region, as you know. Just a simple concept to start with. Let's say we have three resistances. 1 ohm, 98 ohm, 1 ohm. All three in series, so equivalent is 100. The current will be 1 ampere because the EMF is also 100. So I into R is the potential drop, so 1 into 1, and this is 98 into 1, and this is 1 into 1. So we can say that 1 volt is dropped here, 98 volt is dropped here, and 1 volt is dropped here. So when these resistances are in series, the maximum potential drop gets reflected across this high resistance. So similar is the case here when we have connected this battery with this p-type, n-type, and the junction in between, or actually this is the depletion region in between. Now this depletion region is actually depleted of charge carriers that we discussed in the previous class. So since there are very less charge carriers which can actually conduct electricity, so its resistance is very high. So as compared to this p-type part here and this n-type part here, the middle part will have extremely high resistance. So most of the voltage here of the battery that we supply will be reflected across this depletion region only, and very few here on p side and n side. So let's say we apply a small potential difference across this p-n junction. This is also called a diode. We'll discuss why. So yeah, so apply a potential difference. Let's say we apply a potential difference with the help of a battery of EMF 0.1 volt. Alright, so very small voltage. So what happens? Okay, so so this battery would like this point to be at high potential, this point to be at lower potential. So it applies an electric field like this. So this is the E of the battery, and because of the E of the battery there is a potential difference across these 2 points. And what is the total potential difference between these 2 points? Between these 2 points it will be around 0.1 volt. But we know that there is already an electric field existing here because of this space charge region. This electric field, this is the built-in electric field, and this built-in electric field has already created a built-in potential difference of 0.7 volt. So a backward potential drop of 0.7 volt and a forward potential drop of 0.1 volt of the battery. So overall what will be the potential drop? It will be 0.6 as we go from here to here. And so we can say that since the potential difference has decreased and also the net electric field has decreased, because some part of the electric field built in, some part of it will be cancelled by the electric field of the battery. So net electric field in this direction has become reduced, and so the potential difference between these 2 points has got reduced now. Instead of 0.7, now it's around 0.6. And when the potential difference has decreased from this side, between this side and this side, the potential energy of the electron on the p side and potential energy of the electron on the n side, the difference in the potential energy has also reduced, and we say that the barrier height is reduced. So as you can see from this diagram here, so this is the old energy level of the electrons in the conduction band of p side. So let's call this as the lower limit of the conduction band EC, and then this is the EC of n type. So keeping the EC of n type constant, now instead of having this EC, now the EC of the p type will decrease relative to this EC of n type. Similarly the EV will also decrease. So this is the EV of the p type, and this is the EV of the n type. So instead of having the energy gap, this is the old barrier energy gap here, this one, this energy gap will decrease because of lesser electric field. Now let's compare the electrons which were able to diffuse here. So forget about this new, let's compare this electron here and this electron here. Was this electron previously able to drift from diffuse from here to here? Yes. Why? Because there were energy levels here. Energy levels were here above EC. But what about this electron? Well, this electron couldn't diffuse from this side to this side previously. Why? Because this was the upper level EC, and this was the forbidden energy gap. This is the old forbidden energy gap. Old forbidden energy gap. And this electron was not able to diffuse from here to here because there was no energy quantum state here corresponding to its energy. But when this energy EC has dropped down, so this is the new EC. This is the new EC. And so lots and lots of quantum states will be there here also. So can we say now this electron will be able to diffuse? Yes. So we can say that these electrons are extra that can diffuse now from this side to this side, because corresponding to their energy there are quantum states now available, because the entire EC has been dropped down, brought back downwards because of the decrease in the overall electric field. So potential barrier decreased, the barrier height decreased, more and more electrons will be able to diffuse here. So the diffusion current increases. Alright. Now what if we apply instead of 0.1 volt 0.2 volt? Then the barrier height will decrease even further, and so something like this. And so these electrons will also be able to come here, diffuse here. As we keep on decreasing, as we keep on increasing this applied voltage, this comes down here, and as this comes down here, the energy difference between the EC of the p type and EC of the n type, it becomes very less like this. And so lots and lots of electrons are able to diffuse, and this gives rise to a very large diffusion current. So as this external applied voltage is increased, it gives rise to a very high diffusion current. Okay. So coming now to this. So this is what I was explaining previously, that as the energy decreases, we find more and more electrons here. As energy decreases, number of electrons in this energy increases exponentially. So lots and lots of electrons on the lower side, on this lower side, lots and lots of electrons because of high, and electrons having high energy, these are very few, maybe very few. Yeah. So that is what is written over here. Now coming to this drift current. This drift current, which was there previously also. See, in equilibrium, drift current and diffusion current were equal and opposite, and they were cancelling out each other. Now we have understood that because of the decrease in the barrier height, the number of electrons which are able to diffuse now is now tremendously high. So diffusion current has increased. Now another thing is that this diffusion current will increase exponentially with the applied voltage. Why? Because on application of this external applied electric field, externally applied potential difference, this barrier height decreases. The more we apply this external potential difference, the more is the decrease in this energy barrier, and so more and more electrons are able to come.